everyone, in today's video we are going to continue talking about simplifying radicals, but this time we're not just going to work with square roots, we're going to work with nth roots. So we are going to do a little bit of review with simplifying square roots, then we're also going to use variables, and then we're going to move up to higher roots like third and fourth and fifth roots. And we'll also talk about simplifying negative radicands and odd root radicals because it's a little different than the square roots that we've done previously. Okay, so let's go ahead and get started. First, I want to be sure that we are all on the same page with a little bit of vocabulary. So we all hopefully are comfortable with this radical symbol. The thing that's inside this x to the m power, that's called the radicand. It's just the thing inside of the radical. And then the other important vocabulary is the index. The index is the type of root that we are taking. So typically we write a square root, and what we mean by that is that there's a 2 here that's implied. You'll see in this chapter that we'll have cube roots, meaning that it's an index of 3. Fourth roots, which is an index of 4, and so on. Notice that the index is written on this little kind of ledge point part of the radical. Be sure that you're writing it small and you're putting it in that index spot. Okay. So with that vocabulary in mind, we talked when we did simplifying square roots about the product property of radicals. And basically what it says is if you have a number that you can break down into 2 smaller factors, then you can take those radicals separately from one another. The square root of a product equals the product of the square roots of the factors. So let's review what that means. In this first example, I have the square root, that is a 2 implied there, of negative 50. So recall that the first thing that we did was we made a list of factors, numbers that multiply together to get 50. So I'm going to write 1 times 50, and I'm going to go in order here. So then 2 times 25. Now we could keep going and get down to like 5 times 10, but I'm actually going to stop at 2 times 25 because 25 is a perfect number. 25 is 5 squared, and because this is a square root, that's a good thing. So I'm going to rewrite this radical as negative 1 times 2 times 25, rewriting the 50 as 2 times 25. Now I'm going to think about which of these pieces can I take the square root of. The square root of negative 1, we've learned, is the imaginary number I. The square root of 2 does not simplify, so he's going to stay inside of that square root. And then the square root of 25 is 5. Notice that all of these are held together with multiplication. This is 5 times I times the square root of 2. And I did put these in a very particular order. I put my integer first, I put my imaginary number second, and then I put my radical at the end. Let's look at one more of those for a quick review. If I'm taking the square root of negative 48, I'm going to make a list of factors. 1 times 48, 2 times 24, 3 times 16. I'm stopping there because 16 is a perfect square. That means I'm going to rewrite this as negative 1 times 3 times 16. When I simplify, the square root of negative 1 is I, the square root of 3 does not simplify, and the square root of 16 is 4. So that is my simplified answer for that one. That hopefully is a quick and easy review. We're going to move on to some new things now. The first new thing is actually pretty similar to what we've already been doing, but we're going to add variables now. So we're still going to make a list of the perfect squares and keep it in sight, and we're going to factor using the largest perfect square. That part's all the same. And we're going to be doing this with the variables too, and we're going to make sure that no radicand has a factor other than one that's a perfect square. So let's look at that. Let's do the 16 first. We know 16 is 4 times 4, right? So we are going to have a 4 that comes outside of our radical. I'm going to give myself a little space there. X squared, if you think about it, if we're taking a square root, that means we're looking for pairs of x's. And this is a pair of 2 x's multiplied together. So that x squared term the square is going to undo the radical and leave us just with x. So the square root of x squared is x. That comes outside. Then when I look at y to the fourth, remember I'm looking for pairs because this is a square root. And if I have 4 y's all multiplied together, that means then that I have a pair there and a pair there. So I have y squared coming out of that radical. And I didn't leave myself quite enough room, so I'm going to move that. And then my z's are the last thing that I need to look at. If I have 10 z's, so if we break it down kind of the long way for a moment, 5, 6, 7, 8, 9, 10. And I look at how many pairs I have because it's a square root. I have 1, 2, 3, 4, 5 pairs. So that's z to the 5th power coming out. Now I do want you to notice that 2, this exponent of 2, divided by the index 2 is 1. And that's the power on our variable here. 4 divided by 2 is 2. And 10 divided by 2 is 5. So notice here that if the exponent inside of the radicand is divisible by the index, then you can use that division. You don't have to write things out like this. I would certainly recommend not doing that, but instead using that division to help you get there efficiently. And we can do the same thing with things that aren't quite divisible. It's just we have to think about the leftovers. So let's look at a case like that. So with 27, the first thing I'm going to do is make my list of possibilities. 1 times 27, 3 times 9. I'm stopping there because 9 is a perfect square. So that means I have the square root of 3 times 9 times x to the 5th, y to the 8th, z to the 3rd. All right, let's break down these pieces. The square root of 3 does not simplify, so I'm going to leave that inside of my radical. The square root of 9 is 3. The square root of x to the 5th. 5 divided by 2 doesn't quite work, but 4 divided by 2, that's 2, right? So that means that x squared is going to come out, and that dealt with the first 4 of those x's, right? That's that one and that one. This 5th one, he doesn't have a partner in this game, so he stays inside. Y to the 8th, 8 divided by 2 is 4, so y to the 4th comes out. Z to the 3rd, 3 doesn't get divided by 2 evenly, but I can take out one of those pairs. If there's 3 of them, I can take out one pair, and this 3rd one is left on the inside still. So that is our final answer then. All right, so now let's look at doing the same thing, but when the index changes and we don't have square roots anymore. So in this first problem, notice that the index is a 3. So we're taking a cube root this time. It means we're looking for perfect cubes in our list of possibilities, and we're looking for triplets when we look at variables or something that's divisible by 3. So we're going to use the same steps. We're going to make a list of our perfect numbers. We're going to factor using the largest perfect factor of each term. We're going to simplify if we need to. So because this one doesn't have any variables in it, I'm just going to start making my list of factors for 32. I have 1 times 32, I have 2 times 16, and then 4 times 8, and 8 is a perfect number. It's 2 to the 3rd power. So I'm going to rewrite this as the cube root. Don't forget to write the index there because that changes it to a square root if you forget it. Do not forget the index when you rewrite these. And then that's 4 times 8. All right, so the cube root of 4, that doesn't simplify at all. The cube root of 8 is 2. So my final answer is 2 times the cube root of 4. All right, let's look at this next one. This next one has a perfect number in it, 27. That's 3 cubed, so that part's going to be easy. I don't need to make a list of numbers. And I'm also going to have to think about my variables here, things that are divisible by 3 and what leftovers there are. So the first thing I'm going to do is this cube root of 27 is 3, so that comes outside of my cube root. I'm going to draw my cube root and write my cube there on the index so I don't forget about it. X to the 5th, So that's one triplet coming out, but because it doesn't divide nicely, when that triplet comes out, the other two stay inside. So that's x squared still inside. Y to the 8th has two triplets in it, right? Because y squared on the outside, that's like pulling out 6. If we think about that long way again for a moment. 1, 2, 3, 4, 5, 6, 7, 8. This triplet comes out, this triplet comes out. That gives me y squared coming out. These two are left inside, so there's also a y squared inside. And then z to the 3rd, that's one triplet. 3 divided by 3 is 1, so that z comes out and nothing is left inside. Notice here that I'm being really careful to make sure that it doesn't look like the index is the exponent on this z. That is an exponent of 1. Be very clear about your work to make sure that your exponent and your index look separate from one another. All right, let's do one more. This time, though, it's a 4th root. So we're looking for something to the 4th power when we look at our list of perfect numbers. There are no variables, so we don't have to worry about that. All right, so let's go. 32 is 1 times 32. It's also 2 times 16, like we had just a minute ago. 16 is a perfect number, though. It's 2 to the 4th power. So because of that, that makes this one pretty easy to simplify. I'm going to draw my 4th root, not forgetting about my index. I'm writing 2 times 16. The 4th root of 2 stays as it is because that's in simplest form, but the 4th root of 16 is that 2 base from our perfect numbers. So our final answer is 2 times the 4th root of 2. All right, let's do one more of these. This time, notice our index is a 5th root. So we're taking a 5th root, or oh goodness. All right, let's make our list. 64 is our number that we're working with. I'm looking for something raised to the 5th power. 1 times 64 doesn't work. 2 times 32. Oh, and that's good. 32 is 2 to the 5th power. So that means I'm going to be able to rewrite this as the 5th root of 2 times 32 times a to the 3rd times b to the 5th times c to the 24th. Okay, so the 5th root of 2 stays as it is, but the 5th root of 32 is 2, because 2 to the 5th is 32. And then let's look at our variables. A to the 3rd, I don't have a set of 5. There's only 3 a's there, so they're all going to stay inside. None of them are coming out. B to the 5th, 5 divided by 5 is 1, so b to the 1st power comes out. And then c to the 24th, if I had 25, then I'd be able to pull out c to the 5th, but I don't, so I'm only going to pull out c to the 4th, which takes care of 20 of them. But then there's still those 4 more left over, so that's c to the 4th still inside. So my final answer here is 2 times b times c to the 4th, and this is times here. I wrote it kind of far apart. You don't have to give that much space, times the 5th root of 2a to the 3rd, c to the 4th. All right, so the last thing that we need to talk briefly about is when we're simplifying a negative radicand, that means there's a negative inside of the radical, but it's an odd root radical. So we're looking at an odd index in these. When we were doing square roots with a 2 for the index, remember that we defined the imaginary number I to equal the square root of -1. Now, when we have odd radicals or odd root radicals like the cube root, let's think about this for just a second. If I did -1 times -1 times -1, because that's a triplet of -1s. Well, -1 times -1 is +1. And then when I multiply those together, I get -1 again. So that means that -1 to the 3rd power is equal to the same thing, -1. That means then that if I'm trying to simplify the cube root of -1, that's the same thing as simplifying the cube root of -1 to the third power. And that third power and third root undo one another because I have a triplet of -1s. So notice in this problem, I have taken the cube root of a negative number, and there are no imaginary numbers in it because you can take the cube roots of negative numbers. You can take the fifth root of negative numbers. You can take the seventh root of negative numbers. If you have an odd index, you don't have to worry about imaginary numbers. You can pull that negative out because -1 to any odd power is still going to equal -1. All right, so let's look at this next one. If I have the fifth root of -32, that's like the fifth root of -1 times 32. 32 makes me really happy here because I know my perfect numbers, so I know 2 to the fifth is equal to 32, which means that that's going to simplify really nicely. And because it's an odd power, the -1 can come out of the radical as well. So the fifth root of -1 is -1. And the fifth root of 32 is 2. My final answer then is -2. All right, so in this video, you learned how to simplify square roots when they had variables in them as well. You learned how to simplify nth root radicals, like fifth and fourth roots and things like that. And we also simplify negative radicands in odd root radicals without having to use imaginary numbers. So go ahead and try those now you try problems.